For the Introduction to Epidemiology course and the module on measures of association, this is the fourth lecture segment on the precision of measures, for which we represent using confidence intervals. So, what are some approaches to describing random error affecting a study result? In many situations, the confidence interval is preferred over a p-value because it provides more information. Epidemiologists strongly prefer to see a measure represented with a confidence interval rather than a p-value. So what questions could we ask with either one of those things? So, is the observed data different from the null hypothesis? A p-value will tell you that. A risk ratio or an odds ratio with a confidence interval will also tell you that. What are the direction and magnitude of the apparent difference? P-value does not tell you that. A risk ratio or odds ratio with a confidence interval does tell you that. And what values of the measure are unlikely given the data? Risk ratio or odds ratio with confidence interval do a great job of telling you that. So we do prefer a confidence interval over a p-value because there's more information, particularly about what values of the measure are unlikely given the data. So the value of a measure, such as an incidence rate, risk ratio, hazard rate ratio, that we calculate from the observed data can be referred to as the point estimate. So in the previous segments, we set up our little 2x2 table and we calculated a value, and that value we sometimes would say is our point estimate. When we start talking about precision and confidence intervals, we're going to say, okay, that value we calculated from our data is the point estimate, and that's kind of, considered, the value that's most consistent with the data that we observed, clearly. Then the confidence interval describes the random error around that estimate that is attributable to sampling. So the confidence interval is, what are some other values of the odds ratio or risk ratio or hazard rate ratio that are possible given that our sample is not the only sample in the universe, that there could have been other samples that could have arrived at different point estimates. So how do we interpret a confidence interval? So I am not giving you the textbook statistician's definition of a confidence interval. I'm going to tell you how I think about it. A useful way to think about the 95% confidence interval, and frankly, you rarely see any other. It's perfectly possible to calculate a 90% confidence interval, a 99% confidence interval. People don't usually do it. You'll see 95% confidence intervals. So a useful way to think about those is that they are a range of values that are consistent with the data. If the study were repeated 100 times, the true value of the measure would fall within the confidence interval about 95 of those times. And that to me is somehow, that second point is the one I can most easily wrap my brain around. If we kept repeating this study over and over again, the 95% confidence interval is the range that our point estimate would fall in through we could be expected to fall in through all of those replicates. One thing about confidence intervals is that they give you no information about bias. Confidence intervals strictly represent random error related to sampling. So the confidence interval is based on the observed data with its possible biases. The hypothetical 100 replicate studies would be studies that repeat the same biases. So if you have a nice tight confidence interval, but you believe there's a serious bias in a study, the tight confidence interval doesn't really make you feel any better about that bias. If you repeated the study with the same bias, you would have the same wrong answer 95 times, the same biased answer 95 times. So I often see papers that present both a confidence interval and a p-value. I discourage that. The confidence intervals and the p-value are based on the same data and the same concepts. So showing both the p-value and the confidence interval, I believe, is redundant. So this is a graphic that comes out of the Rothman textbook, Rothman epidemiology textbook. So first of all, he's showing you that a p-value, what a p-value represents in terms of the range of possible values for a risk ratio. So the top of the mountain, that little point, is your point estimate. So given the data that you've sampled and calculated that point estimate from, that is the most likely value, so it's getting the highest probability. And then other values of the relative risk moving away from that, moving to the right and left on the relative risk scale, are somewhat less likely given the data that you have observed. And the null hypothesis, or 1 on the relative risk scale, is shown with a vertical line here. And this particular hypothetical sample, the curve crosses the null value of 1 at a p-value of 0.08. So this curve generates the compatibility of the observed data with different values of a relative risk, and then p-values are used to help capture that random error. So same curve, but now we're showing some confidence intervals superimposed on it. So in this case, the 95% confidence interval at the bottom, the right end of that is above 10, and the left end of it is just slightly below 1. Because remember, the p-value was 0.08, did not achieve a p-value of 0.05, so the 95% confidence interval would cross 1 exactly if the p-value was 0.05. So a point being here that there's a range of possible values of your measure that are possible given your observed data, and either the p-value or the 95% confidence interval can be used to try to describe that, and they're really based on the same concept. Another just piece of epidemiology trivia is that relative risks, risk ratios, odds ratios are symmetrical on a log scale. If you're looking at the horizontal axis, they're symmetrical on a log scale, not on a straight arithmetic scale. So another issue about representing confidence intervals, I'm going to return to the same two examples that I showed when we were discussing odds ratios and how to set up a table and things like that. So this table shows 95% confidence intervals around these odds ratios on the far right. And in this study, we observed for the row that says less than 5 years ago, so individuals who had used oral contraceptives within 5 years, those cases had a somewhat higher odds of exposure. Sorry, cases who, if we look at only people who, at cases who were exposed to contraceptives within 5 years, and then controls and how many reported using oral contraceptives within 5 years. So the odds of exposure was higher among cases than controls, yielding an odds ratio of 1.27. And the confidence interval on that estimate was 0.99 to 1.63. So that is just slightly not significant, statistically significant. If the odds ratio, if the confidence interval excludes 1, that represents statistical significance at the p equals 0.05 level. I'll say that again. If the 95% confidence interval on a ratio measure excludes 1, then the result is statistically significant at the 0.05 level. So this did not exclude 1. So just for a little bit of background, there's a number of other studies that would indicate that any risk of breast cancer, increased risk of breast cancer associated with oral contraceptive use, usually is among individuals who have used them within 5 years. And so because most women who are using oral contraceptives are quite young, and the risk of breast cancer is quite low at those young ages, that many people find an odds ratio of 1.2 or so increased risk of breast cancer during those years that you're quite young. That relative increase on an existing very low risk of breast cancer, most people find that to be an acceptable risk. So we could have just said this so this finding by itself was not very exciting, but it was quite consistent with other literature. So had we not shown the odds ratio and just shown a p-value, the p-value would have been 0.06 or something like that. But the reason the odds ratio gives you more information is that even with just our study alone, well, gee, what's the likely sort of upper limit of the value of the odds ratio? What could the odds ratio really be? And that higher end, that 1.63, makes you think, okay, so the oral contraceptive use within 5 years is very unlikely to increase the risk of breast cancer as much as 75 or 80%, or doubling the risk. And again, since we're talking about young women among whom the risk of breast cancer is fairly low, looking at that confidence interval and understanding that the upper limit is also fairly low is good information. And that's kind of an example of why we feel like putting a confidence interval rather than a p-value is giving the reader more information. Okay, and this example is also one that we saw before earlier in this lecture, where we're talking about an example of a strategy that I do not recommend for how to set up a table. So in the far right, besides giving us an odds ratio and a confidence interval, this paper also gives us a p-value for each of those same comparisons. And if we go down the list and we remember that this is a 95% confidence interval, and that if the confidence interval excludes 1, that's equivalent to significance at the 0.05 level, it's not that surprising that the first row of data, where the confidence interval is 1.01 to 7.4, so just barely excluding 1 from that confidence interval, well, the p-value is 0.05. The second row of data, where the odds ratio is 1.09 and the confidence interval is 1.09 to 1.12, well, that excludes 1, and actually it excludes the lower limit is not all that close to 1, and that p-value is 0.01. And going down the list to diabetes with an odds ratio of 1.57 and a confidence interval of 0.99 to 2.51, so 1 does fall. The value of 1 does fall within that confidence interval, so it's not significant at the 0.05 value. In fact, the p-value is 0.06. So this table, I feel like, is making my point that the p-value and the confidence interval are based on the same data, and they are really, in terms of statistical significance, they are telling you the same thing. So I would say that none of these p-values really needed to be shown in this table. I feel like they're redundant of the information about statistical significance that we can already see in the confidence intervals. So the formula for a confidence interval for a risk ratio. Believe me, I am not expecting in this introductory epidemiology class that you will be able to remember or reproduce this formula. I can't reproduce this formula. I have to look it up every time. But I'm showing it to you because I want us to think about what are the characteristics of your study design that are going to influence your confidence interval. So what this is saying from left to right is that the natural log of the risk ratio at the lower confidence interval and the natural log of the risk ratio at the upper confidence interval are equal to the natural log of the risk ratio point estimate plus or minus z times the standard deviation or standard error, which I believe in this case are the same thing, times the natural log of the risk ratio. So what does all this mean? Let's start with z. Z is just a statistical constant. For a 95% confidence interval, or alpha equals 0.05, z is 1.96. It just is. I will not get into that any further. It's a constant. Okay. Then that standard error or standard deviation, where does okay, so going back to some other parts. The risk ratio, of course, depends on the difference in the disease frequency between the exposed and the unexposed. So the farther your point estimate risk ratio is from 1, the farther your confidence intervals are going to be from 1. That's fairly intuitive. Okay, and that leaves us with the standard error. So what does the standard error depend on? It depends on the N. It depends on the number of observations, the number of people you've collected data on for your study. But it also depends on the proportion exposed versus non-exposed and the proportion diseased versus non-diseased. So the next part that I'm going to show you, I'm trying to make a point here. Don't worry about this. So this is the standard error. It's the square root of 1 over A, which is the number of people exposed individuals who have the outcome, minus 1 over N, which is the number of people in the exposed group, plus 1 over C minus 1 over N0, so C being the number of people with the outcome in the unexposed group. So these are the reciprocals of the cell sizes. So the reason I'm showing you this is just the one point that I want to make is that if you have a very small cell, I mean, suppose you've studied 5,000 people, but what if only 5% of them are exposed? And what if the disease incidence is very low, so they only have like 6 people in your yes exposed and yes outcome cell? That one value being in the denominator, your standard error is going to be related to the inverse of that value. So that any very small cell is going to really increase your standard error. So even if your total stuff, so the whole point of showing you this calculation, I had to look it up, believe me, I can't remember it. The point is, even if your N is large, even if your total number of people that you observe is large, if one of those cells, A or B, is very small, this is going to drive up your standard error and make your confidence intervals wide. So it's always something to think about when designing studies, not only studies of people, not only the total number of people, but if one of your things, either your disease or your exposure, is infrequent in your population, that is going to adversely affect your statistical power and your confidence intervals. And one other point that I said something about earlier, but I found this nice graphic in the Rothman textbook that I think also helps make the point, that if you have a systematic error or bias in your study, increasing your study size doesn't change that. A flaw in your study design that results in a bias, quantitative bias, if you study more people using the same flawed study design, the magnitude of that error stays the same. So that's the horizontal line, systematic error or bias. And then the line that is curving from left to right and going down and getting smaller and smaller is the random error. So as your sample size gets larger, that definitely will reduce your random error, tighten your confidence intervals, but it doesn't fix your biases or your systematic errors.